All right, so in line with what we were just discussing in terms of the fact that the electron not only has orbital angular momentum as it circles the nucleus, it also has a spin angular momentum that is associated with the fact that the electron has something that's equivalent to spin. Now, it's not quite the same thing as spin. You could imagine an electron to be a uniform sphere of charge in which you could slice up all of the volume of this electron into different disks, and then within each disk you could have as this thing turns with an angular frequency omega, you could have a magnetic dipole moment that is due to each of the little rings, thin rings of charge within each disk, and then add all of those together. And then that would give you a magnetic moment for a uniform sphere of charge that was rotating. And so, but that's not what an electron is. According to the Standard Model, an electron is a point charge. And so it doesn't have any physical extent. Now, the fact that the Standard Model doesn't give it any physical extent and says it essentially is a point particle is, I think, a problem. Because there, at a certain point, has to be a fuzziness as to how big or small something is that is based on the uncertainty principle. And so to say something has zero size means that you know exactly how big it is. But if you know exactly how big it is, then you're not going to know what its momentum is, how fast it's spinning. And so I think that there probably is a size, but that it maybe is on the order of the Planck length. Nevertheless, this model for electron spin fails in a number of respects if we try to look at it too carefully, because the electron is way smaller than could be explained in terms of a uniform sphere of charge if it were to produce the observed values for the angular, the spin angular momentum. It would have to be traveling faster than the speed of light. And also, if you have a spin axis that's up, and then you rotate it by 180 degrees, then it would be spin down. If you rotate it by another 180 degrees, spin up again. But an electron, you have to rotate it through, 360 degree rotation turns it into a spin down electron. You have to rotate it by two 360 degree turns to bring it back to a spin up electron. So the electron is seeing a different number of dimensions than we're seeing. And if we use this classical model, where it's a uniform sphere of charge that's rotating, the observed magnetic moment could only be produced by an object that's rotating faster than the speed of light. And so whatever this is, it acts a little bit like spin. It smells like spin, looks like spin, but it isn't really spin. Nevertheless, it's a solution that Dirac came up with for the relativistic Schrödinger equation, in which he used this expression for the total energy. E squared is equal to p squared c squared plus m naught squared c to the fourth. And then he tried to find the square root of this and couldn't factor this properly. Okay, and so in other words, you need to come up with some kind of a perfect square before you can solve the Schrödinger equation, because the momentum and the rest energy can't be separated unless there is some kind of a factorization that can be made. And so what he used was four-dimensional imaginary matrices, which is, I think, kind of an obvious solution to the problem. And what he discovered is that something pops out that looks a lot like spin. And so it gave you an additional quantum number, and that quantum number then, under the influence of the orbital angular momentum, the spin angular momentum vector, which points in the same direction as mu, can project onto the vertical axis, so that this is mu, and spin to an SZ that's equal to plus 1/2 h bar, but it can also project down here to a minus SZ. And we talked about this a little bit before, minus h bar over 2. Okay, and so we have the same kind of splitting then of the spin angular momentum that we have for the orbital angular momentum. But the external magnetic field in this case is produced by the orbital angular momentum. So this is called the spin-orbit interaction. And in fact, it's this spin-orbit interaction that defines the filling order for the electrons in terms of the Emsevelle number that I outlined for you before on the periodic table. It's the magnetic field produced by the orbital angular momentum that interacts with the spin and causes the spin values to split. And so this then allows for the spin down electron to come in first, and then the spin up electron can come in into the same quantum state because it has a different spin quantum number. As I indicated before. And so it's this spin-orbit interaction that is really truly responsible for the filling order being Emsevelle equals -1, 0, +1 for spin down, then -1, 0, +1 for spin up. Okay. So that being said, we can look now at these two different solutions, one with a spin down and one with a spin up, and we see why this doubles the number of allowed solutions for the Schrödinger equation and completely specifies the property of matter on the periodic table, because we now have double the number of solutions that we had before with just the quantum numbers n, L, and Emsevelle. But with m sub s, we can have new values that's equal to plus and minus 1/2. Okay, so with that thought in mind, let's take a look at molecular solutions. And when we look at molecular solutions, we should consider the simplest of all possible molecules first, that being the H2 plus molecule. Okay, so the Schrödinger equation allows for the solution for molecules too, not just for atoms, but for combinations of atomic wave functions. And the reason why this is the simplest of all possible molecules is with an ionization of +1, there's only a single electron that holds together the H2 molecule from the two individual H2 atoms. So here's one H2 atom, here's the other H2 atom, and so somehow then these two different H2 atoms are going to have to share the electron between them. And then that is going to need to result in bonding. And so what we, first of all, need to understand about molecules is, and this was stated, I think, quite clearly by Richard Feynman, if the net attractive forces are greater than the net repulsive forces, then a molecule will form. It's as simple as that. If you can add together all of the attractive forces, and those attractive forces are larger than the repulsive forces, then you can get a molecule. But if the net repulsive force is greater than the net attractive force, then no molecule forms. So the question then is, how do we want to share an electron between these two, in which these two protons, in such a way that the attractive forces are greater than the repulsive forces? Well, that's just from a classical point of view, without even getting into quantum mechanics yet. Let's put the electron at the midpoint between the two. And let's look at the net attractive forces of these two protons on each other. Okay? Well, we're going to get a very strong attractive force of positive to negative. And that's going to be 4 times bigger than the repulsive force between positive and positive. And similarly, because of symmetry, on this side, the net attractive force of this positive on that negative, because it's an inverse square law, and you have the same amount of charge here as you do between here and there, that means that the attractive forces should be 4 times greater than the repulsive forces, and so this should then hold this molecule together. On the other hand, what if you put the electron out here? So that the electron spends more of its time outside of the center between these two. Then the electron is going to pull on the proton here, and that's going to create a very strong force. And then you're also going to get the repulsion between the two positives. And so this one is going to move away from that one. This one is going to attract this one, but the repulsion is going to be greater between positive and positive. And so although the two effects here are not exactly the same, as was the case here, the net effect is to make the two protons fly apart. And so even if we look at this thing quantum mechanically, I think that we can perhaps convince ourselves that a probability density function in which the electron spends more time between the two protons is going to create bonding, whereas if the electron spends less time between and more time farther away, that's going to create less bonding. Excuse me. So now let's look at the solutions to the Schrödinger equation. Well, we know that for a single 1s orbit, the psi looks like something like, it's 4, 2 over a naught to the 3/2 power, something like this, e to the minus r over a naught. And so this decaying exponential function is going to look something like this. And similarly, if the electron is circling around this atom, then you're going to get this kind of a wave function for this solution as well. So this is just the two individual solutions to the Schrödinger equation for an electron orbiting around both hydrogen atoms. And then those would be added together. And so we can see that then on this slide here as the top solution. And so that's our psi symmetric. And then the bottom solution is our psi antisymmetric. So it turns out that the psi antisymmetric is the one in which we add essentially the negative of the wave function together, and the symmetric solution is one in which we add the positive values of the wave function together. And for our spatial solution, we can have either one of these as an allowed solution to the Schrödinger wave equation. So what I need to do first, before I can fully explain this properly, is to define symmetric and antisymmetric in general. So a symmetric function, not worrying yet about whether this is a wave function or just any kind of a function. Symmetric function is sometimes called an even function. Because if you write, say, y as x to some power, then n has to be an even number. So this is an example then of a symmetric function. It's y equals x to the n, where n is an even number. And so let's say, for example, that y equals x squared. Then n would be 2. What if y equals x cubed? Or I'm sorry, y equals x to the 4th, not x cubed. X cubed would be an odd number. Y equals x to the 4th would look something like this, but would cross over at the points 1, 1. And it would go up faster for x greater than 1, but it would go down faster for x less than 1. And then you could also have here y equals x to the 100th power. It would be almost like a vertical line coming straight down and then going straight across and then straight back up again. So we see then that a symmetric function here, or an even function, is one that has symmetry about the vertical axis. And so I think that you can see that that's what we have here. If we add together these two wave functions, then in the middle, it's going to look something like this. And so about this line that goes through the midpoint between the two protons, I'll get the electron out of the way now, because this is the probability density function for the electron. We see that this psi function is going to result in an electron that spends more time, because it has more probability of being between the two atoms and less probability of being outside, which is the argument that we made before with our classical example of putting the electron right in between. So what we want is more probability of the electron between the two atoms. And so that corresponds to what we, in general, define as a symmetric wave function. Now what's an antisymmetric wave function? Well, antisymmetric would be like y equals x to the n, where n is an odd integer. So for example, y equals x. Y equals x to the first power. Or y equals x cubed would look something like this. So that would be an odd integer again. Or we could have y equals x to the 101 power, look like this, and then drop straight down. So it kind of be like a, whereas this is more like a box, y equals x to the 100, y equals x to the 101 would be like a box that's in the middle is kind of tweaked and turned inside out. So this would be y equals x to the 101 power. So we can see then that the basic properties of these is if we reflect about the x-axis and then reflect about the y-axis, we get the rest of the function. And so here it's just a single reflection about the y-axis, but here it's a reflection about the y and then a reflection about the x, and so we say that this one has symmetry about the origin. And so, why am I making such a big deal about this if all that we really need to know is that the electron spends more time between the two atoms? Well, associated with that, we must have a spatial wave function where the spatial solution looks something like this, that is symmetric. But there is also another kind of a troublesome constraint on these, and this is referred to as the Pauli exclusion principle. I say troublesome because it involves a lot of symmetry, but not troublesome from the standpoint of what it represents, because what it really does is it gives uniqueness to all of the elements on the periodic table. It makes them different from each other. And so what the Pauli exclusion principle tells us is that an electron must exist as an antisymmetric total wave function. And this applies to spin 1/2 particles, which we'll see later is what we call fermions. So the total wave function for a particle like an electron that is a spin 1/2 particle is antisymmetric. And so here we see that the electron is in a symmetric spatial state. Okay? But we don't have to worry about the electron sharing this space with another electron. But what if we were to go to the H2 molecule? It now has 2 electrons. It's not ionized anymore. Now, the total wave function for the particles that are associated with these 2 electrons must be antisymmetric. But we must still have a spatial symmetric part for both of them. Because if the electrons are each being shared by the 2 protons, then they want to spend more time between, which is associated with a symmetric function. Okay, and so how can we resolve that? Well, we can resolve it by making the spins different. And so we can say then that psi total is equal to psi spatial times psi spin. So the spatial part can be symmetric, and the spin part can be antisymmetric. So by antisymmetric here, basically what I'm saying is that the spin part, when multiplied by the spatial part, can give us a total wave function that's antisymmetric. While still maintaining a symmetric spatial. Okay, so by antisymmetric, we're just saying that the spins have to be different. here, and that will, if the spins are the same, then this wave function can't exist. Okay, and so why is a symmetric times an antisymmetric wave function equal to an antisymmetric wave function? Well, you can see that's simply enough just by taking x squared, that's a symmetric function, by what we looked at before, multiplying that by x cubed, it gives us x to the fifth. So this is symmetric. This is antisymmetric. And the product is then antisymmetric. Because an even number plus an odd number will always give us an odd number. Okay, and so as long as we have a spatial wave function that reinforces the probability that the electrons can spend more time between the two atoms, then the spin part can be different and can be associated with an antisymmetric wave function. So let me just give you a way of expressing this. This is the way that we express composite wave functions. So this would be for two electrons. We can say that psi total is equal to psi one, psi 2. This is quantum numbers NL, M sub L, and M sub S, which I'll just call here alpha. And here this would be alpha prime. Okay, so in other words, alpha here might be a set of quantum numbers N, L, M sub L, M sub S, plus M sub S. And alpha prime, or we could call it beta. Let's call it beta. Beta would be N, L, M sub L minus M sub S. So in other words, alpha is not equal to beta because of the fact that the spin quantum number in this case might be plus 1/2, and in this case it would be minus 1/2. And so then we will subtract from that for an antisymmetric wave function. Psi alpha of 2, psi beta of 1. And then, as it turns out, there's also a normalization constant out in front that looks like 1 over the square root of 2. So this is our psi total. And this is the way we write it for an antisymmetric wave function. So what we notice here then is if alpha equals beta, psi is 0. Then that means the spins are aligned. And psi total equals 0. And so what the Pauli exclusion principle tells us then is that if the quantum numbers are the same with electrons 1 and 2, they can exist in the same spatial state. And so there's an effective repulsion. This exclusion then gives us 0 probability of finding the electron when alpha and beta are equal. And so this prevents electrons from occupying the same set of quantum numbers with other electrons. And so we say, well, of course the electrons can't occupy the same state because they're negative and they would repel each other. But that isn't really what this is telling us. What this is telling us is something much stranger than that. This is what we call an entangled state, in which particles 1 and 2 are in an inseparable combination of quantum numbers alpha and beta. And so there's no way to separate these out. And in the overall expression for the wave function, we say that the particles, until they're measured, do not have separate identities. And they're entangled. So why is the Pauli exclusion principle true? Well, it's been observed to be true. And so this mathematical relationship was discovered by Pauli. But we're not exactly sure why it's true. But the particles are, when they're entangled like this, there's no separate identity between the two electrons, for example, that would be orbiting around the H2 atom. Okay? And so if alpha isn't equal to beta, then we get a value for psi total that's not equal to 0. So the electrons then fill up the energy states with one particle per energy state. And so if this weren't the case, let's think about what this would mean to the periodic table. If you could have electrons that could all go into the same quantum state, so that this might correspond, say, what if this were a plus sign there? Then that would correspond to a symmetric total wave function, rather than an anti-symmetric one. If that were the case, and that is the case, by the way, with, say, helium in a superfluid. You can get helium atoms all together in one spot, basically all occupying the same spatial state and all in the same quantum state. But if you tried to do this for atoms, then in, say, the 1s orbit for hydrogen, you could have 1,000 electrons in that one state. That means that every atom would have a different property from every other atom. And if that's the case, then there'd be no consistency to the properties of matter, and life couldn't exist, and that kind of a disordered universe would make any kind of atomic forms that have any kind of consistency impossible. Okay? And so this then allows for us to still have a symmetric spatial state as long as the spin states are different. And so if we go back up, this is kind of a long interlude between the symmetric state and the antisymmetric spatial state. We see here that the antisymmetric spatial state is not one that gives rise to bonding. Okay? And so you could have an antisymmetric spatial and have symmetric spin in which both spins were the same. But that won't give rise to bonding. So the only kind of solution that give rise to bonding is one in which we have the symmetric spatial and the antisymmetric spin, so that the spins don't match up. And so here, if we add these together and you bring the atoms a little bit closer together, we see that there's more and more probability between the two protons for the symmetric state, but for the antisymmetric state, they tend to cancel out. So most of the probability is found outside of the atoms, which gives rise to anti-bonding. And it's not really psi, of course, that we're looking at here, but psi squared. So when we square that, that gives rise to a very small probability for something that is where the spatial state is antisymmetric. There's very little chance of finding the electrons between the two atoms. Whereas here in the symmetric spatial, the electrons spend lots of time between the two atoms and can give rise to bonding. Okay, so this applies not only to the consistency of elements on the periodic table, but also to other systems. For example, with a white dwarf. In a white dwarf star, and we believe that our sun will eventually become a white dwarf, we essentially have a carbon core, which is the result of helium fusion in the end states of a star's evolution. And then the helium fuses into carbon. But at this point, the electrons are basically torn off of the carbon nuclei, and the electrons, because they're less dense, float to the surface of the star. So this generates an electron shell. And so what I tell my students in my astronomy class is that the electrons repel each other. And that's what prevents the shell from cracking. And that's what keeps the white dwarf at about the size of the Earth. So this is what our sun will become, is something that's the size of the Earth. But with a density that's about 1,000,000 times the density of water. Okay? But what I don't tell them in my astronomy class, but which I'm telling you now, is that it's not just the electron repulsive forces that are at work here. It's the fact that these electrons can't occupy the same set of quantum numbers. And so that means that if they were to stand right on top of each other, that the alpha and the betas would be the same. And that would cancel out the total wave function, would make it zero. So it's by conservation of probability, if they're not on top of each other, they've got to be somewhere else. But if they have to be somewhere else, that creates an effective repulsion. And that effective repulsion is called the exchange force. So this exchange force, then, is what holds the electron shell solid. Now, it's not just two electrons, so you'd have alpha, beta, gamma, and you'd have a couple 100 million of these, and they would be in a composite antisymmetric wave function which would have 100 million electrons in it. And so you'd have to take a determinant of something that is just huge, multidimensional, to express it, but it still works the same way as it does for two single particles, like the ones that we were looking at for either for a particular orbit in an atom, or for the electrons in circling an atom in a molecule. And so here then, this prevents the carbon core from collapsing, and so we end up then with what's called degenerate electron pressure. This is the exchange force that is caused by the Pauli exclusion principle.